All right, with this problem, I have the choices, which of the following statements about the series is true. It's got to be one of these four. So let's check real quick. The series diverges by the nth term test. If I use the nth term test, I'm looking at the limit as n approaches infinity of the formula itself. And if n is approaching infinity, 1 over n is approaching 0, and the sign of 0 is 0. So that fails, or basically it shows that you cannot use the limit that you cannot use the nth term test for divergence. It is inconclusive. Now, the other options were issues with comparing that series to 1 over n or to n. Well, let's keep in mind that no matter what I put into a sine function, its absolute value is always less than or equal to 1. But to do a comparison test, I have to have a series with positive terms only. But if I look at the numbers that I'm dealing with, I am looking at the sign of 1, the sign of 1/2, the sign of 1/3. And if I'm looking at the graph of sine x, and I know that this peak is pi over 2, which is already bigger than 1. 1 is about right there. So the values I'm getting out of sine are only these positive values. So I don't need the absolute value sign. And I'm looking at a beginning to thinking about how I'm going to compare this. Now, they only gave me two options. They gave me that I'm going to compare it to either 1 over n, or I'm going to compare it to n. Let's say I compare it to n. Who's bigger, n or a number that is shrinking to 0? Well, n is definitely bigger. N is going to diverge by the nth term test for divergence. I need my series of positive numbers to be greater than the terms of a series that diverges if I have a divergent situation. I have a divergent situation, inequality is not the way that I want it to go. So I am not going to be comparing it to n. 1 over n. Now, if I'm going to use the direct comparison test, I need to be certain that this divergent series, I know 1 over n is divergent, I need to be certain that the sign of 1 over n is bigger than 1 over n. It isn't, and to show you that it isn't, I'm bringing out Desmos. I have this already zoomed in quite a bit to be able to show you that while I'm wanting the red sine of 1 over x to be greater than 1 over x, that's not my situation. I'm seeing less than. And I have severely zoomed in on this graph. I'm going to now zoom back out a bit so you can see where we are looking. And just kind of realize that they are extremely close. But if I really zoom in, I'm going to find out that the sign of 1 over x is actually smaller. The direct comparison test will not work. So that means that I'm going to take a look at the limit comparison test. With the limit comparison test, if I choose to compare to the divergent harmonic series 1 over n, then I need to check the limit as n approaches infinity of my series divided by who I'm comparing it to. Now, right now, that may not look familiar to you, but you are expected to be familiar with a particular limit. And that particular and very specific limit is if I have the sine of x and I divide it by x, and I look at the limit as x approaches 0. I can show, and actually I could quickly do a L'Hopital to show that this is equal to 1. But this is supposed to be a familiar limit that you recognize. But we've got a 0 versus an infinity, but do you see the flippy-floppy situation? Well, when n approaches infinity, 1 over n approaches 0. So this is actually equal to the limit as x approaches 0 of sine x over x, which I happen to know is 1. So by the limit comparison test, because this answer is not 0 and not infinity, so basically it's greater than 0 and finite, I am allowed to compare it to 1 over n. They both converge or they both diverge. That diverges, therefore, I can say that the series diverges by the limit comparison test to this series. And I showed you with the Desmos graph that you cannot use the direct comparison test. That's not going to work. We saw that we cannot use the nth term test for divergence. And then with this last one, you're not going to be able to do limit comparison with just plain n. You are not going to be able to get that finite non-zero answer to a limit.